Okay, guys, back again. We're going to continue talking about covalent bonds, but now we're going to talk about the difference or go into more about polar covalent bonds. When we last left off, we talked about uh, that every single covalent bond that we had talked about previously had been a non-polar covalent bond because the electrons were being shared equally. But we want now to talk about a polar covalent bond and how to create a polar covalent bond. So remember, in a polar covalent bond, the electrons are shared unequally. So in a polar covalent bond, we know that at least one atom has a small ionization potential. And having a small ionization potential, meaning that that particular atom would have a willingness to lose the electron. Now we know if it's a polar covalent bond, it's not going to totally lose it, but the end of that particular molecule will tend to have its electron drawn away from it. Okay, so we know that if that electron is being drawn away from this particular atom, then we know also that this is going to be the positive or the more positive end of the molecule. Now, next, you have an atom who has a large value for electron affinity. And so we're saying that this end of the molecule is more likely to have a stronger draw or pull on the electron. Okay, so not that, because remember we're still talking about polar covalent bonds or covalent bonds, so we're still sharing the pair of electrons, we're just sharing that pair of electrons unequally. So we know that if I am pulling this electron who is negatively charged closer to myself, then my end of the molecule is going to be more negative. Okay, so that's going to be the negative end. Now, Linus Pauling says that every single atom has an ability to draw an electron or have a pull on the electrons. Okay, and we want to call this ability to pull or attract electrons electronegativity. Okay, so again, we said the ability to attract or pull or have a draw on an electron is called electronegativity. So, especially when we're uh, talking about these bonds, we know that the uh, element with the higher electronegativity value will win the tug of war. So now what we need to do is look at some of the trends for electronegativity. So if you have your periodic tables, and if you're looking from the bottom left, which would be francium towards uh, fluorine, uh, we know that you're going to increase in electronegativity. If we start at the top, for example, at hydrogen, when we go down to potassium or even further down the table, it says we're going to decrease in electronegativity. If we simply just move from the left side to the right side, we're going to increase in electronegativity. And then, of course, metals have low electronegativity, and then nonmetals are going to have high electronegativity. So let's go on and let's take a look see at water, because we know that water is a polar molecule. Now, the thing that you see is these positive and negative charges. So you ought to be able to guess who has a stronger pull on the electrons. And then we need to add something to this charge, because these are not whole charges like you would find in an ionic bond. Nobody totally gave up or took an electron. They're being shared unequally. All right, so here's my covalent bond. And so it's showing us that the electrons are being drawn more towards the oxygen. Okay. So it says that oxygen is going to be more negative. So it's not a complete charge, it's actually a partial charge. So it's going to be partially negative, which is going to make the hydrogens partially positive. Okay? So the hydrogens are partially positive, the oxygen is partially negative. So if a question were asked, why is water a polar molecule, we could say because oxygen has and think about it. Look at where oxygen is located in the table. Okay? It's on the far right. We said if we move from right to left, we increase in electronegativity values. Okay? So oxygen has a higher electronegativity value than hydrogen. Therefore, oxygen has a stronger draw or pull pull on the let's just say on hydrogen's electrons, therefore making the oxygen partially negative and the hydrogens partially positive. I had to abbreviate, ran out of room. All right, so that's why water is a polar molecule. Okay? Now, let's move on to ionic bonding. Sometimes ionic bonds are considered to be completely polar, and the reason being is because the atom's electrons are being completely transferred from one atom over to another atom. So completely polar. All right, so it says when electrons are transferred from one atom to another, we form ionic bonds. So let's look at our rules and see who ionic bonds form between. So we can have strong electron donors. And if we have a strong electron donor, we know that that electron donor has one or two electrons in its outer shell. One or two electrons in its outer shell, because I'm going to donate because it's easier for me to give up one or two than to take 6 or 7. So then that tells us that a strong electron acceptor would have 6 or 7 electrons in its outer shell. Okay? So what we want to look at then is, as an example of ionic bonding, is table salt, sodium chloride. So in order to uh, complete this task, we will need to know the stats of each of those atoms, sodium and chlorine. Okay, so I'm going to run down the stats and then we'll move to the next slide. So we know the stats for sodium, so Na, are the atomic number. If you're looking at your tables for sodium is 11, so the atomic number is 11. The atomic mass, and remember to use the rounded atomic weight, is 23. So the number of protons we know comes from the atomic number. So that's equal to 11. At this point in our drawing, we know to be the electrons are equal to 11 because at this point we're electrically neutral. And then the number of neutrons, if you remember, we're going to get those from taking the mass minus the atomic number, or in which also represents protons. That's going to give us 23 minus 12 is equal to, 23 minus 11 is equal to 12. We're going to do the same thing for chlorine. Chlorine's atomic number, if you remember, is what? 17. The atomic mass is equal to 35. The number of protons, 17. Electrons, 17. 35 minus 17 gives us neutrons is equal to 18. Okay, so now that we have the stats, you can see where I have begun to draw the Bohr model. And here is sodium. And here is chlorine. Remember, because chlorine has 6 or 7 in its outer shell, we want to say that this guy is going to be the acceptor, and sodium, because it has 1 or 2, is going to be the donor. Okay? Alright, so the next thing that we see is that sodium will donate his lone electron to chlorine, who has 7, 2, 3, 6, 7 electrons in its outermost shell, or in its valence shell. Now, one of the things that's going to happen is when he donates this lone electron, so there's going to be a charge imbalance, okay? Why would there be a charge imbalance? Because if you remember, and I'll just do one of them and you'll get the picture for the other one, but sodium had 11, sodium had 11 protons, and he also had 11 electrons. It was electrically neutral, but he has given one away, so you have 11 protons and now only 10 electrons. So now he's going to become a +1. So we'll see that in just a minute. All right. So he's donating, and let's move on to the next slide, which we've already been there like 12 times. All right. So it says that sodium would have a +1 charge because he lost one of his electrons. Chlorine picked it up. So now he has a total of 8 electrons in his outer shell. So chlorine will be a -1. Okay? So the other label that you'll need is that sodium becomes the what? It is the cation, and chlorine is negative, so it becomes the who? The anion. Okay, it says, well, how are the two atoms held together? We know that ionic compounds are held together simply by the attraction occurring between the negatively and positively charged ions that are helping to create this ionic bond. All right, we'll stop right here and we'll pick up with hydrogen bonding next time.